we call it binary search. Okay, binary, do you remember? Binary represents for 0 and 1, right? So if a book, we always divide it to half, and then search in the half, and you determine in which half, and then divide it into half too, one more time. And this kind of algorithm, we call it binary search. Okay, so we say binary search is kind of algorithm. Always search begins at the middle. Okay, begins at the middle. And finds the item or eliminate half of the unexamined items. Eliminate them, okay? Throw them away, okay? And then process is repeated. Okay, repeated. It is a kind of receiving. Okay, repeat this task only on a half where the item might be. So we call it a binary search. So let's check if we write a pseudocode for binary search, what it's supposed to do. So firstly, we set some labels. Like first, we define where is first, and we define where is the last. In an array, we need to know where is the first, and we need to define where is the last. Okay, this is the first flag, this is the last flag. So we can calculate a middle, right? A middle equals the first one plus the last one and divided by 2. And we find this position. And we need a length, right? You need to know how long is this list. So firstly, we have a length. Remember, it's from 0 to length minus 1. So at the first beginning, we say the first equals 0. So the first is here. And we set the last equals to length minus 1. Okay. And also we need a found. Is that found or not a flag? Firstly, we set it to false. It's not found. If it's found, we set it true. Okay. Usually we use 0 in the computer to represent false and 1 to represent true. It's a binary value. Then we need to loop, right? We always find half of them. So firstly, in which situation we do the loop? In which situation we do the loop? If the first is smaller than last, okay, first is here and last is here. So we can find the first will move here and last will move in this direction. So if first is still smaller than last, it means the task is not finished. If the first is equal or larger than last, then it means all the items has been examined. So this is the first AND condition. And another AND condition is we set a flag found. If it's not all the list has not been examined thoroughly, then one has been found, then it is also okay. Okay, so we have 2 AND conditions. And each time we have set middle. Middle is another flag, okay? Middle is here, it's middle. We set it to this one first. Then we check if it is found. If yes, then it's true. If no, then we check if it is larger or smaller. If larger, then move the first to here, first flag to here, and you check in this area. If it is smaller, then you move the last flag to here, and you check in this area. So we need to make a decision. You to check if this is okay or satisfied or not. If it is okay, then we set. If it is smaller, right, smaller, then the first one doesn't move. We just move the last one to the middle. Okay, so we set last as middle minus 1. Okay, we will move it to here. Okay, set here as the last. So else we move the first to here, right? So we set first to middle plus 1. And we do this loop until all the lists are examined, or in which place we have found that element. So it's a while loop. And finally, what do we return? What's the result? Do you remember for this question, what's the result? The result is supposed to be if you find something or not, right? Is this element in this list or not? So finally we return found. This flag tells you it is found or not found, the element in this list or not in this list. So this is the result. And also, if you want to know which position have you found, you also can find that, right? The item can equals to which one, and then that with the middle position at that time, when you're out of the loop, it is the final position you want to find. Okay, so this is the pseudocode about this binary search. To search in this table, in this table, the elements are arranged by the characters. Okay, so check it from A to B, A, B, C, D, E, F, G. Okay, from A. Here is not C. It's another. It's an error here. Okay, just consider it like J. Okay, anything, just a mistake. Okay. Anyway, it is an ordered array, and it is ordered in an ascending order due to the characters, the first number of the characters. And now we need to search. So firstly, if we want to search cat in this table, and use binary cat. Binary search, binary cat. Use binary search to do that. How do we do? Remember we set 3 mark, right? We set first, last, and middle to represent the position. So first, we list the first is 0 and last is 10. So right, 0, 10, and middle. Use 0 plus 10 divided by 2. Okay. So we can get the middle. So you find the number in the middle to compare it with cat. Okay, you compare it. And it's not. And obviously C is smaller than D. So remember, if it is smaller, we move the last, okay? So it is smaller than D, so we doesn't change the first, and we move the last equals middle minus 1 and write it here. And then we use 0 plus 4 divided by 2, get a 2 in the middle. That is here. Okay, it's in this area. And compare one more time. So C is equal and A is smaller than H. So it is smaller, still smaller. So we modify the last to middle minus 1. And calculate it, get a new middle, okay? So it is 0. And we check if this one is smaller or larger. In fact, it's larger, okay? So mistake here. C is obviously larger than A. So this time, we do not change the last. We modify the first and modify it as middle plus 1. So we have first, last, and middle. 1 plus 1 divided by 2 equals 1. So the first one in this position is cat. So we compare it. It's right. So we can return it is found. So if we need to search cat, we need 4 steps using binary search. Similar, let's check if we want to search fish. How many times do we need? So first, the last, and the middle, and check the larger. So we modify the first equals middle plus 1. And it is smaller, so middle minus 1 to the last. And then get the middle, and it's correct. So we need 3 steps to find the fish. Okay, fish is here. To search these 3 steps. And cat is here. It needs 4 steps. And similar for zebra. Zebra is not in this list, right? So we similar do it. We use the first, the last, and the middle, and we compare it's large. Then we modify the first to plus 1. And when compare, similar, you do the loop. And until finally, the first is larger than the last. Okay, so that is in a table. The first is larger than the last. If this list or array exists, the first will never larger than the last. But if this situation happens, that means all of your table has been checked. So just return false. So this is another AND condition here. Okay, remember, another AND condition. Either it is found or the first is larger than last. So we can find through 5 steps, we'll figure out zebra is not in this list. So this is an example about this binary search. Okay. Okay, so we listed here the comparison between sequential search and binary search. If the length is 10, and what's the average number of comparisons would we have? And the average, so because in sequential search, the smallest is 1 time. The last is, the maximum is 10 times. So the average is always like this. But in the binary search, the average number of comparison, you can find this is much smaller than the sequential search. So we can say, is the binary search better, right? Better here, represented in this table. Then we have a question is that, is the binary search always better than the sequential search? Is this true or false?
Yeah, that is, binary search is not always better than the sequential search, right? It depends on the real situations.
Search, the result is 4 times. But if we use sequential search, we only need 2, right? So in this kind of situation, binary search is not always better. Okay. So another question is, a binary search can be applied to both a sorted array and unsorted array. Is that true or false? It's obviously false, okay? It's false. Binary search can only be applied to sorted array, cannot be applied to unsorted array. And another is binary search is always faster than a linear search. Is that true or false? It's false, okay? We